This is problem set 31. We're going to talk about percent composition, empirical formulas, and molecular formulas. So let's start off with a pretty simple percent composition problem. This is a mass percent composition, which is what all of your problems will be. So this is asking, give the percent composition by mass for each of the hydrocarbons below. Unless otherwise specified, assume percent composition is always the mass percent, which two have the same percent composition. So percent composition of carbon, it doesn't say of carbon, but we're going to find that of carbon, and then everything else will be hydrogen, right? So these are percents, so they have to add up to 100. And so I'm pretty much just going to find, how much carbon is in this molecule divided by the total amount, the total mass in this molecule. So I've got 6 carbons, so 6 times 12, divided by my total, which is 6 carbons plus 6 hydrogens. And I can plug that in. When I do, I get carbon. This is going to be 92.3% carbon, which is going to leave it as 7.7% hydrogen. This one is 2 carbons divided by 2 carbons and 4 hydrogens, which gives me 85.7% carbon, which leaves me with 14.3% hydrogen. Here we have 3 carbons divided by my total, which is 3 carbons plus 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, which gives me 81.8%, which leaves me with 18.2% hydrogen. And lastly, I have 6 carbons divided by my total of 6 carbons plus 12 hydrogens, is 85.7% carbon, and that leaves 14.3% hydrogen. So which have the same percent composition? These two have the same percent composition, because you can see this is C2H4 and this is C6H12. So this is a perfect multiple of this guy, which is why they end up with the same percent composition. All right. Ancient Egyptians used lead compounds such as lead sulfite, lead carbonate, lead as pigments in cosmetics, and many people suffered from chronic lead poisoning as a result. Calculate the percentage of lead in each of these compounds. All right, so first off, I'm just going to pull up my periodic table, because we'll need a lot of molar masses here. So for PBS, we've got 1 lead, and lead weighs 207.2. divided by the whole molar mass, which is the lead, plus the sulfur, which is 32. Which gives me a percent of 86.6% lead, that first one. The second one is PbCO3. It's going to be my 1 lead atom divided by lead plus carbon plus 3 oxygens. And that gives me 77.5% lead. And lastly, I've got my 2 leads, so Pb2Cl2CO3. I've got 2 leads divided by 2 leads plus 2 chlorines plus a carbon plus 3 oxygens. So my mass of lead divided by the total mass. When I do that math, I get 76.0% lead. There we go. So that was calculating the percent of lead in each of the compounds. All right, the following organic compounds have been detected in space. Which of them contain the greatest percentage of carbon by mass? Let's just find the mass percents for each. That's going to be the amount of carbon. So 10 carbons in this one divided by 10 carbons plus 8 hydrogens. This one gives me 93.75% carbon. This is 18 carbons divided by 18 carbons plus 12 hydrogens. 94.7% carbon. Okay, next is this one. We've got 22 carbons divided by 22 carbons plus 14 hydrogens. That gave me 94.96 is what I got there. And pyrene is 16 carbons divided by the total. And that gives me 95.05% carbon. So what has the highest? Pyrene has the greatest percent of carbon by mass. Okay, so that was a lot of practice calculating mass percents. All right, unlike most metals, gold occurs in nature as the pure element. Miners in California in 1949 searched for gold nuggets and gold dust in stream beds, where the denser gold could be easily separated from sand and gravel. However, larger deposits of gold are found in veins of rocks and can be separated chemically in a two-step process. Okay. If there's 23 kilograms of ore and it's 0.19% gold, how much zinc is needed to react with the gold in the ore? Okay, so you got to imagine I've got a big chunk of ore, okay, and in that ore you've got, make my colors there, like some veins of gold. All right, so the ore is not a chemical. Ore is just like, I don't know what, it's just a bunch of different minerals stuck together. It's a mixture. It's not a chemical formula. So nothing in this equation is ore, okay? But what we're going to do is we're going to grind this up and we're going to put it in this NaCN solution with oxygen and water, right? And the gold is going to react. All the rest of the rocks and junk and stuff is just going to stay in solution, so nothing's going to happen to it. But the gold is going to react and get stuck in this compound. We then take that compound, react it with zinc, and then we can get the gold to come out by itself. Okay, so the gold isn't bonded to anything in the rocks. It's just mixed up in a way that makes it hard to isolate it. And so we do this process. So we're trying to find how much zinc is needed to get all of the gold. Well, how much gold do we have? Well, we have 23 kilograms of ore, and it's 0.19, so 0.0019. 0.19% is 0.0019 gold. Okay, so how much gold do we have? 0.043 0.37 kilograms of gold, which I'm just going to change to 43.7 grams. Okay, that's how much gold we have. Okay, now we want to convert that to zinc to see how much zinc we would need to get all of that gold. So we have 43.7 grams of gold. If we want to use the equations, we've got to switch to moles. And 1 mole of gold is 196.97 grams of gold. Now I got 2 steps here. I take gold to this thing and then this thing to zinc. So I know from the first reaction that 4 moles of gold make 4 moles of NaAuCN2. The second reaction tells me that 2 moles of NaAuCN2 requires 1 mole of zinc. And I want to know how much zinc I need, so why don't I just change that into grams? 1 mole of zinc weighs 65.38 grams. And that tells me I need 7.25 grams of zinc in order to get this percent of gold out of that much ore. There we go. All right. Give the empirical and molecular formulas for the 5 oxides of nitrogen in A and hydrocarbons in B. Which molecules have the same empirical formulas? Do any have the same percent composition? Okay, so looking at this, you should, just so you know, blue is nitrogen, and so therefore red is oxygen. So let's take a minute and talk about, well, molecular formulas. We know molecular formulas. Molecular formula here molecular formulas here is easy. I've got 2 nitrogens, I've got 5 oxygens. Right here I have 2 nitrogens, I have 4 oxygens, 1 nitrogen, 1 oxygen, 2 nitrogens, 3 oxygens, 1 nitrogen, 2 oxygens. The empirical formula is the most reduced ratio. So what I mean by that is, and the reason it's called empirical is it's what we can observe empirically. If I just take a bunch of, let's say, N2O4, if I take a bunch of that and I measure how much nitrogen's in it and how much oxygen's in it, and I just take the ratio of nitrogen to oxygen, the best I can measure is NO2. I'll know that for each oxygen there's 2 nitrogens. But without looking at one molecule, I won't be able to know that there's actually 2 nitrogens and 4 oxygens. I'll just know that there's twice as many oxygens as nitrogen. So the empirical formula is the molecular formula reduced down as low as it can go. Okay, so in this case, can we reduce this? Nope, there's nothing I can divide by, so it's going to stay N2O5. This is already reduced. It's going to stay N2O3, but this one is also going to stay NO2 because it's already as reduced as it can go. So which molecules have the same empirical formulas? These guys have the same empirical formulas. Do any have the same percent composition? Yes, these also have the same percent composition because they each have 1 nitrogen for every 2 oxygens. Okay, so that's a relationship that this problem is trying to get you to understand. All right, so let's do this now. Molecular and our empirical. Okay, my molecular is C2H6. So my empirical would be that reduced, which would just be CH3. This would be C2H4, so the empirical would be CH2. C2H2, so the empirical is CH. So in this case, none of these have the same empirical formula, and therefore none of them have the same percent composition. Okay, so more about empirical formulas. How do we calculate an empirical formula from stuff that we can measure? So medical implants and high-quality jewelry atoms for body piercings are frequently made of a material known as G23 titanium or surgical-grade titanium. The percent composition of the material is 64.39% titanium, 24.19% aluminum, and 11.42% vanadium. What is the empirical formula of the surgical-grade titanium? Okay, so the empirical formula is just the simplest ratio of molecules or moles of your atoms in your molecule. So, ratio of atoms or moles in your molecule. So we need to figure out, we collected a bunch of this surgical grade titanium, and we figured out this is what we have in our collection. We need to change that into moles so that we can find mole ratios to get our empirical formula. So this is kind of a systematic process. I'm going to write down the steps. So first, we're going to assume 100 grams. Then we're going to convert grams to moles. Then we're going to divide everything by the smallest number. And then we're going to multiply everything to get whole numbers. So let's see what that looks like. So why do we assume 100 grams? Could we assume any amount of grams? Sure. But we assume 100 grams because then these percents just turn right into grams. So we have 64.39 grams of titanium, 24.19 grams of aluminum, and 11.42 grams of vanadium. Okay, so but this now gives us grams, but we want mole ratios, so we're going to change these grams into moles. Okay, so titanium's molar mass is 47.87. Aluminum's molar mass is 26.98. And vanadium's molar mass is 50.94. Okay, so if I get all those into moles, okay, I get 1.345 moles titanium. I get 0.8966 moles of aluminum, and I get 0.2242 moles, 43 moles of vanadium. All right, so technically, now that I've gotten the moles, I could say that my formula is titanium 1.345, aluminum 0.8966, and vanadium 0.2243. Okay, but that's gross, and we don't do that. We like to have whole numbers. Well, the easiest way to make sure that we don't have any numbers smaller than 0, right, I should say first, we want whole numbers, so we got to multiply all of these by something to get whole numbers. Easiest way to make sure we don't have anything less than 1 is just divide by the smallest value that you have. Okay, so that's step 3, divide by the smallest number, so that in our amount of moles that we have, the smallest that we get is 1. So when I do that, I'm going to have 1 here. Here I get 3.997, which is essentially 4. And then here I get 5.996, which is essentially 6. What that tells me is that I now have this equation, Ti6 aluminum 4 vanadium 1. There we go. So we've found the empirical formula. Now, is this the molecular formula? I don't know. This is the most reduced form of the molecular formula. Maybe we'll talk about how to figure out the molecular formula from this later. Now, it's important to carry out decimals, especially in your molecular masses here, because otherwise these numbers might not be as close to integers as you would like them to be convinced that they are integers. Because the last step is that if you get, let's say that I did this problem and I got 4.5 here. Okay, I can't have that, after I divided by the smallest, I got 4.5. I can't have that fraction. But because it's half, what I can do is I can multiply everything by 2, and I get titanium 12, aluminum 9, vanadium 2. Okay, so that's that last step, multiply to get whole numbers. Okay, you're going to multiply by 2 or by 3 or by 4 to get whole numbers. That's not the case here, so I'll erase it. In this case, we didn't have to multiply by anything to get whole numbers. All right, let's do some more. Inhalation of asbestos fibers may lead to lung disease, known as asbestosis, and to a form of lung cancer called mesothelioma. One form of asbestos chrysotile is 26.31% magnesium, 20.27% silicon, 1.45% hydrogen, and the rest is oxygen. What's the empirical formula? All right, let's do it. So we're going to assume 100 grams, so we can just change our percents to mass. We have 20.27 grams of silicon, 1.45 grams of hydrogen, and the rest is oxygen. So it has to add up to 100, so let's figure out. That gives me 51.97 grams of oxygen. Now I gotta change, use 15.999 grams of oxygen. 1 mole of hydrogen is 1.0079 grams of hydrogen. Gotta switch to moles. Okay, magnesium is 24.305. And silicon is 28.085. Like I said, carry out your decimals so that you get nice, clean integers at the end of your problem. So we're going to change all these to moles. I got 1.083 moles of magnesium, 0.7217 moles silicon, 1.439 moles of hydrogen, and 3.248 moles of oxygen. Then we got to get these nice numbers, we're going to divide by the smallest, which in this case 0.7217. I do that. Here I get 1.502. It's going to be 1. It's going to be 1.994 and 4.500. Okay, so obviously, so this is like 1.5, 1, 2, 4.5. I need whole numbers though, so I'm going to multiply everything by 2 because I've got these halves. 9, 4, 2, 3. So my empirical formula is magnesium 3, silicon 2, hydrogen 4, oxygen 9. So there you see the whole process. Percent to mass, mass to moles, divide by the smallest number, and then multiply until you get whole numbers. Awesome. All right, number 7. An unknown organic compound has the simplest formula, CH2. If its molecular weight is 28 grams per mole, what's its molecular formula? Okay, so we know that the empirical is just the molecular divided until you get the smallest numbers possible. So that means that the empirical times some number gives me my molecular. How do we figure out what that number is? Okay, well, we know the molecular formula has the molecular weight is 28 grams per mole. Well, what's the empirical formula's mass? Well, CH2 is going to be 14 grams per mole. Well, what do I have to multiply by to get that to equal? 2. So that means that C2H4, which is my empirical, multiplied by 2, okay, right, the empirical formula of this is C2 or CH4, and the molecular weight of this is 28. And I figured out what I needed to multiply by looking at the molecular weight versus the empirical weight. Okay, so C2H4 would be my answer there. Benzene, a common solvent, has a covalent molecular compound which contains only carbon and hydrogen. Its simplest empirical formula is CH, and it has a molecular weight of to 2 significant digits of 78 grams per mole. Okay, so this is the empirical formula. What's the molecular weight of this? Or what's the weight of this empirical formula? It is going to be 13 grams per mole, but the molecular formula is 78. So I need to multiply this CH by something in order to get a molecule with a mass of 78. Well, what do I need to multiply it by? Well, it's 78 divided by 13 gives me 6, which means I need to multiply this CH by 6, which means I'm going to get C6H6. Awesome. All right. The material often used to make artificial bones is the same material that gives natural bones their strength. Its common name is hydroxyapatite, and its formula is calcium 5-phosphate 3OH. Propose a systematic name for this compound. This isn't the type of naming that we cover once you have 3 ions in there. But one reasonable answer to this question is you could have, you could say, I don't know, you said calcium triphosphate monohydroxide. All right, calcium, 3 phosphates, 1 hydroxide. Figure out how many calcium based on the charges. I don't know. That's not naming that we teach in this course, so it's not really something to worry about. What's the mass percentage of calcium? All right, so we've done this before. So we have 5 calciums. Calcium has a mass of 40.1 divided by my total mass, which would be 5 calciums, 3 phosphoruses, 31, 12 oxygens, actually 13 oxygens, and 1 hydrogen. And I got that we get a mass percent of 39.9% calcium. When treated with hydrogen fluoride, hydroxyapatite becomes fluorapatite, this guy, an even stronger substance. Does the percent mass of calcium increase or decrease as a result of the substitution? All right, so does the percent mass increase or decrease? Well, there's only 2 things I can change. I can change the amount of calcium, and I can change the total mass. In this case, the amount of calcium doesn't change, but the total mass does because I replace a hydroxide group with fluorine. So when I switch that hydroxide group, which weighs 17 grams per mole, with my fluorine, and fluorine weighs 19 grams per mole, well, the result of that is that the total mass is going to go up because I switched this OH with the F. Total mass goes up, which means the percent mass goes down. Obviously not by much, but it will go down. All right. Give brief answers to the following questions about combustion analysis. Let's talk a little bit about combustion analysis. We use combustion analysis to identify substances, specifically hydrocarbons, that we don't know much about, or we don't know what they are. So let's say I've just got this powder. What I can do is I can get my powder, I can burn it, I can flood in a bunch of oxygen, we'll call this our O2 valve, put in a bunch of oxygen, burn that hydrocarbon, and then collect all of the gases. And we can collect our CO2, and then we can collect our water, right? Because when we burn hydrocarbons, we get carbon dioxide and water. So I burn it, and I collect all my carbon dioxide and all my water that I get afterwards. So I've got this hydrocarbon C something, H something, O something, plus oxygen, giving CO2 and water. Okay. Now, I don't know what my substance is, but what we're going to do is we're going to find the empirical formula. Now, if you remember, when we were doing empirical formulas up here, we needed to get our mass of each thing in the compound, and then we could change mass to moles divided by the smallest, right? We need to get the mass. So that's our goal here, is from this information, we're going to get some amount of CO2 and some amount of water. Well, what we can do is this amount of CO2 that we get, we can calculate in that amount of CO2 how many grams of carbon are there, because all of the carbon came from here. So then we would have our grams of carbon in our starting substance. We can then use our amount of water and figure out how much hydrogen is there, because all the hydrogen came from our starting substance. Now we can't do the same for oxygen because we're adding oxygen, but if we know how much mass we started with and we know how much carbon and hydrogen there is, then we can find the oxygen. And then we'll have our mass, we can change to moles divided by the smallest. So let's answer some of these questions with that brief overview. Is it important for combustion analysis to be done in an excess of oxygen? Yes, because we get complete combustion. Okay, we want to burn everything that we have. Otherwise, the amount of carbon in this CO2, if there's still some of this left, okay, then the amount of carbon in our CO2 won't exactly match how much carbon we started with. So we need complete combustion. So we need to have excess oxygen that we can burn so that our hydrocarbon is our limiting reactant. Can the quantity of CO2 obtained in a material analysis be a direct measure of the oxygen content of the starting material? Why or why not? Nope. First off, there's oxygen in the water. Second, we're adding oxygen. Right? And so for those two reasons, you can't just look at the amount of oxygen and carbon dioxide to figure out how much oxygen you started with. Can the results of combustion analysis ever give the true molecular formula of a compound? Sure. If the empirical formula equals the molecular formula. Right, so what we're going to be doing here is finding the empirical formula. So it's not always the molecular formula, but in the case that it is, then we'll also be finding the molecular formula. All right, what additional information is needed to determine a molecular formula if the empirical formula is known from the combustion analysis? We did this earlier. We would need the molecular mass to figure out what we need to multiply by in order to get the molecular formula. All right, charcoal and propane are used as fuel in backyard grills. Write a balanced chemical equation for the complete combustion of C and of C3H8. So carbon, if we're combusting, we're adding oxygen, and we're going to get CO2. C3H8, we're also combusting it, so we're adding oxygen. We're going to get CO2. We're also going to get water in this case because there's hydrogen in the compound. Need a balance, so 3 carbons, we need 8 oxygens, so that gives us a 4 there. Or sorry, 8 hydrogens. That means 6 plus 4 gives 10, so we need a 5 oxygens right there. Right, how many grams of carbon dioxide are produced from burning 500 grams of the 2 fuels? All right, easy. We've done a lot of this. So we've got 500 grams of carbon, and we want to convert it to carbon dioxide. We got to get to moles if we want to use the equation. 1 mole of carbon is 12 grams. And the equation tells us 1 mole of carbon makes 1 mole of CO2. And 1 mole of CO2 weighs 44 grams. So that tells me I'm going to get 1833 grams of CO2. Now I can do 500 grams of my other substance, C3H8. Okay, 1 mole of C3H8 is 44 grams. And my equation tells me that 1 mole of C3H8 makes 3 moles of carbon dioxide. And then I know 1 mole CO2 is 44 grams. So 500 grams C3H8 is going to make 1,500 grams of CO2. All right. The compound geraniol is on the U.S. Food and Drug Administration's generally recognized as safe list and can be used in foods and personal care products. By itself, geraniol has a rose-like odor, but it is frequently blended with other scents to produce a fruity fragrance. The fruity fragrances of some personal care products. Complete combustion of 175 milligrams of geraniol produces that much CO2 and this much water. What's the empirical formula? All right, so this is our combustion analysis problem. So we have geraniol. We don't know the formula of it, so we're going to burn it. We got CO2, water. Now we can't balance this equation because we don't know what these subscripts are, but we don't need to balance it, so we're going to use combustion analysis. So we have 0.175 grams of this stuff, and we get 0.499 grams of CO2 and 0.184 grams of water. So let's take our amount of CO2 and let's convert it just into grams of carbon so that we know how much carbon we started with. Okay, well, I know 1 mole of CO2 is 44 grams. And based on just the formula for CO2, I know that 1 mole of CO2 has 1 mole of carbon in it, right? Because it has 1 right there. And then I can say I know 1 mole of carbon is 12 grams. So now I found that in that CO2, after I completely burned my stuff, I got 13.6 grams of carbon. Okay, so now I know, sorry, it shouldn't be 13, sorry, not 13.6, 0.136 grams of carbon. Well, now I know that this starting compound had 0.136 grams of carbon in it. Well, let's try hydrogen. Well, I know my water is 0.184 grams of hydrogen, of water. I can get that into moles. Okay, and now, based on my formula for water, 1 mole of water has 2 moles of hydrogen atoms in it. And I know 1 mole of hydrogen weighs 1 gram. Okay, so now 0.184 divided by 18 times 2, that gives me 0.0204 grams of hydrogen. Okay, was that everything? Well, I might have oxygen. I don't know if I have oxygen, but I know that I started with 0.175 grams. So if I subtract my carbon and I subtract my hydrogen, then I'll get 0.0186, and that is going to have to be my grams of oxygen, because that's all else that I could have. So I'm going to add that right here. All right, so now we have our grams of each thing, so now we can find the empirical formula. Move this up. Right, and to find the empirical formula, we need to take grams, oh, I don't need lines that long, grams to moles, divide by the smallest. Many moles of carbon, this many moles of hydrogen, this many moles of oxygen. Now I'm going to divide by the smallest, which in this case is the oxygen. Okay, about 9.7. And 1. Okay, so because I know what the answer is, I can look at this and see that maybe I made a mistake somewhere. So let me just run through my math one more time and see if I can find the mistake. So this highlighted a good concern that you should have when you're doing these problems is I didn't take out my molar masses very far in this problem, and that caused me problems down the road. So if I had taken out my molar masses, this would be about 0.0206, okay, and this would be 0.0184. Yep. So when I do that, so these numbers, that one's fine, but these are going to be incorrect. These are going to be wrong. So let's do it again and see if we get better numbers this time. The way to avoid what I just did is to, when you're doing combustion analysis and any empirical formula problems, carry out your decimals. And divided by the smallest. Gives me 9.84. 17.74. And 1. Now these also aren't very good. I think this is a poorly designed problem because the answer should be carbon 10, hydrogen 18, oxygen 1. Okay, now I would not, this may be close enough to claim 10. I don't think this is close enough to claim 18. I think that this would make me want to multiply by 4. I think this is a poorly designed problem. You can rest assured that anything that you see on an exam is going to be much cleaner than this, even when you do drag out your decimals. Okay, combustion analysis reveals that a certain organic compound with a molecular mass of 62.1 grams per mole has this percent mass. What are its empirical and molecular formulas? Okay, so they give us percent masses, so we assume 100 grams, so 38.7 grams of carbon. And 9.7 grams of hydrogen. Learned my lesson, I'm going to use long decimals now. Okay. I get 3.222 moles carbon, 9.624 moles hydrogen, 3.225 moles oxygen. Divide by my smallest, which is 3.222. That gives me 2.987, and this gives me 1.001. Okay, so these are pretty much whole numbers. I'm going to have C as my empirical formula, C1H3O1. But it's asking, oh, that's empirical, awesome. But now it wants molecular. Well, we have the molecular mass, so I know the molecular mass is 62.1 grams per mole. The mass of this compound of my empirical formula is 12 plus 3 plus 16 is 31 grams per mole. So this is equal to about 2. So my molecular formula is going to be I got to multiply everything by 2. C2H6O2. That's going to be my molecular, based on the molecular mass. All right, 0.225 grams of caproic acid. What do we have left here? 12 and B, and 13. Awesome. 0.225 grams of caproic acid is analyzed by combustion analysis. We get carbon, we get carbon dioxide and water. We have the molecular mass, so let's find the empirical and molecular formulas. Okay, so we're going to, again, use our amount of carbon dioxide to find how much carbon is in our molecule, amount of water to find how much hydrogen. The difference is going to be oxygen, and then we can find the empirical formula, and then since we have the molecular mass, we can find the molecular formula. So we're going to carry out our decimals. Hopefully this one turns out better than our previous one. Then our water. Water is, man, I didn't even carry them out. Look at me. All right, carbon dioxide is 14.03027. Water is, wait, no it's not. Sorry. There we go. 44.009. water is 18.015. All right. I get, let's see, this is number 12, okay. 0.1397 grams carbon, 0.02339 grams of hydrogen. I started with 0.225, so if I take 0.225, subtract my 0.1397, and subtract my 0.02339, I get that many grams of oxygen. Now I have my grams of each thing. I can convert to moles. Moles carbon. Moles of hydrogen and this many moles oxygen. Let's divide by the smallest, which is oxygen. So 1 there. There we go. These numbers are much nicer. So this tells me my empirical formula is going to be C3H6O. Now the molar mass is 116. So let's find the mass of this guy. The molecular weight here is 3 times 12 plus 6 plus 16. So molecular weight is 58 grams per mole. The actual one's 116 grams per mole. Well, 116 divided by 58 gives me 2. So my molecular formula is C6H12O2. So now we've used combustion analysis to find how many grams of carbon, hydrogen, and oxygen were in my caproic acid that I started with. Converted those to moles, divided by the smallest to get mole ratios. That gave me my empirical formula, which I then multiplied by 2 to get a molecular formula with the same empirical formula and the molar mass given in the problem. All right, we could do the same thing again. All right, so we have 0.110 grams of carbon dioxide. I already found all my molecular weights up here, 44.009. And then 1 mole of CO2 is 1 mole of carbon, which has a molar mass 12.011. Okay, I have 0.0225 grams of water. Water's molecular mass is 18.015. Mole of water has 2 moles of hydrogen. 1 mole hydrogen is 1.0079 grams. moles of carbon, grams carbon. Grams of hydrogen. I started with my 0.0405 grams total. I subtract my carbon, subtract my hydrogen, and I get, and I get my oxygen. Now I have grams, I want to go to moles. Carbon, moles hydrogen, moles oxygen, divide by my smallest, which is my oxygen. And what do I get? This is going to be 1. This gives me 5.019. This gives me 5.022. So my empirical formula is going to be C5H5O. Okay, and then my molecular formula, this C5H5O has a mass of 81. This has a mass of 162, so what do I need to multiply by? Got to multiply by 2. So C10 is 10O2. Awesome. Good problem. Good practice problem. And we see how these numbers here and here work out really nicely. That this example up here is kind of funky. Maybe I did something wrong, but I think the numbers are just kind of funky. You should be given problems with clear numbers. All right, last problem. .2 grams of an unknown gas occupies 5.3 liters at that temperature and pressure. What's the molar mass of this gas? Oh, this is pretty easy compared to what we've done before. So my favorite way to think about this is I know that molecular weight is grams per mole. Well, I know my grams. So now I've got to find my moles. And because they give me a volume, temperature, and a pressure, I can use the ideal gas law. Moles in PV over RT. Pressure is 7042, but I'm going to change it to atmospheres, divided by 760. My volume is 5.3 liters, 0.08206, and the temperature is 40 plus 273, which is 313 Kelvin. And that gave me moles of, let's see, I got, oh, there we go, 0.201 moles. So 0.201 moles. Means my molecular weight is going to be 26.2 divided by the number of moles, molecular weight of 130. That's my molecular weight. And then it says further studies indicate this gas is monatomic, so just one atom. So what do you expect it to be with a molecular weight of 130? That's going to be probably xenon. Okay, combustion analysis of unknown gas, given empirical formula CH2. If 2.1 grams of this gas occupies this volume at this temperature and this pressure, what's the molecular formula? So the idea here is if we have an empirical formula, to get the molecular formula, we need the molecular mass. We just showed in part A how to get the molecular mass from this type of information. So the molecular weight is going to equal grams per mole, grams over moles, I should say. Here we have 2.1 grams. Let's find our moles from this information. Well, we know that moles is PV over RT. Pressure is 0.5 atmospheres, 3.1 liters. Ideal gas constant, and 373. That gives me 0.0506 moles. So now I can find my molecular weight is 41.5 grams per mole. Okay, well, what is the molecular weight of this CH2? Oops. So CH2 is going to be 14 grams per mole. So that 41.5 divided by 14 gives me 2.96. So I need to multiply the CH2 by 3, which would give me C3H6. Okay, that's a beefy problem set about combustion analysis, about empirical formulas, and about percent composition.